let's have a little summary on Sturm-Liouville eigenvalue problems. And these are these equations and boundary conditions. It's called eigenvalue problem because the problem is to find lambda and phi. You need to find both, the lambdas and the phis, which solve this problem. Now, when it comes to examples, etc., you need to identify the p, the q, and the sigma, and the alpha 1, the beta 1, the alpha 2, beta 2. And then there are certain conditions that p and sigma are positive, for example, which then can easily be checked. Now, these Sturm-Liouville problems have a wonderful property which is summarized in this mega theorem right here. So the eigenvalues are sorted, lambda 1 less than lambda 2 less than lambda 3, etc., where lambda 1, the smallest one, is called the leading eigenvalue. The eigenvalues are real and they have no limit. So the limit for n to infinity of the lambdas is infinity. They're unbounded. Now, for each lambda n, the corresponding eigenfunction phi n has exactly n minus 1 zeros. And we know this from sine and cosine functions. If you plot them out and count their zeros, then you see this makes a lot of sense. Once we have the phi n, they form an orthogonal basis. And we can write functions as a generalized Fourier series as a sum of a n phi n. Okay, so we expand the function f in this new basis phi n. These are orthogonal with respect to the inner product with the weight sigma. Okay, so the integral or the inner product phi n phi m is equal to the integral from a to b phi n phi m sigma dx. So don't forget the sigma for the general Sturm-Liouville problem. And then, like in Fourier series, we had this convergence result that whenever f is continuous, the generalized Fourier series converges to that value, and if there's a jump, it converges to the midpoint of the jump, so to the half value of f of x from the left plus f of x from the right. Another interesting bit which we found was the Rayleigh quotient. So here is the Sturm-Liouville problem again, but underneath here is the Rayleigh quotient, which is well, an interesting construction of integrals, etc. So here you see it's important to identify the p of x, the q of x, the sigma of x, because they are input right here. They appear right here in this Rayleigh quotient. But once you know them, you can then work with it and try to estimate the leading eigenvalue. And first of all, if phi n is an eigenfunction, then the Rayleigh quotient of phi n is the corresponding eigenvalue. So this is one way how to compute the lambda n once you know the phi n's. But even more so here, the smallest of these Rayleigh quotients is the leading eigenvalue. And the smallest means in the class of all functions that satisfy the boundary condition. So you can just test functions that satisfy the boundary. You do not need to solve the equation to find a good estimate for lambda 1.